Hi everyone and welcome to a new video about control system topics. In this video we will discuss the approximation of a transfer function, and this is our example number 1. In this example again we will look at the calculation step by step and we will verify these in MATLAB simulations. So before we move on with our example, let's first briefly discuss what an approximation is, and we will start with a simple method. And the simple method has the following approach. You need to consider the insignificant poles in your transfer function, in your system, and you need to return your DC gain. So what does it mean actually? So let's look at an example. We have the following transfer function given, which is a third order system, has a pole at -3, -5 and also -40. You can also see that in this root locus plot, which shows you the poles of the system in a unity gain feedback configuration. So what you see is you have the pole at -40 here, which is far away, and you have also two other poles which are very close to the vertical axis, -5 and also -3. So these are the two poles which will actually dominate the transient and also the steady state response of your system. But let's look at what we need to do. We can neglect the impact of this pole at -40 because it is very far away. In this case it is at least 8 times farther away than this pole at -5, and it is of course also much farther away than this -3. So we can then say the following, and we of course need to retain also the DC gain such that the steady state response of the system is the same. So by removing or by actually deleting this pole at -4t, we need to of course have a reduced system, which will be then this system. So in order to retain also the DC gain, we divide actually the numerator by this 40, so you will actually have 4/40, and you will remove your pole at -40, so you will actually remove this third term in the denominator. So you will have actually this expression, which is then the reduced form. And that is just a very simple approximation method, and that is done actually the final result. But in other examples, for example, if you have the following transfer function, then you have h is equal to very close to that one, but the third pole is now at -10, which is not really that far away compared to these two poles. And if you want to now look at the dynamics of the system approximated in this method, you will not have a very accurate result. So in this case we cannot neglect the impact of this pole at -10, since it is just only 2 or 3.33 times far away. So the rule of thumb is in engineering, in the control system engineering, is to have a pole which is at least 5 times far away, which is of course just a rule of thumb. It doesn't mean that you have a guarantee that your system will be very accurate. But in this case we cannot use the simplified or the brute force method to approximate actually this transfer function. Okay, there's also a little bit complicated approximation method which will give you a more accurate result if you have a little bit closer poles to each other. So how does this work? Now it attempts to match the frequency response as closely as possible. So we have the actual system, so strictly speaking it is an algebraic manipulation. So we have this expression, very general form of a system. So we have the zeros in the numerator, we have the poles in the denominator, and we have also the constant k in front of it. This is what we have, and you can see also that in which the poles are in the left of plane, and we need to have that the m, which is the number of zeros, must be equal to or less than the number of poles. That is actually the condition. But if you want to have a lower order or an approximate form of your transfer function, that can be also written mathematically in this form, which is very similar to that one. So this is actually a higher order and this is actually a lower order approximation. So what you then have is, of course, again, the number of zeros must be smaller than the number of poles in this lower order approximation, but it must be also lower than the number of poles in the actual original system. So in order to have an approximation. So this is the mathematical way to look at it. Okay, the gain constant, which is a very important thing here, the k, also with the k here, is the same in the original and also the approximate system. So that ensures actually that you have the same steady state response. So based on that, we can also say, looking at the parameters c and d, which is actually in the approximate transfer function, that must be determined in such a way that this transfer function has a frequency response which is very close to the actual transfer function of the original system. Now, that can be done in this form. So you can write actually by stating the following expression. You can say the original transfer function divided by the approximate transfer function must have actually a value which is very close to unity. So it's required you need to actually have a deviation which is very small from unity, of course in the frequency domain. Now the c and the d, the coefficients from this lower approximation, can be then determined using this and this expressions, which will be of course clarified also later on in an example. In addition, we have more work to do, because these are determined where we have the m and also the delta. The m is the numerator and delta is the denominator of this polynomial. So you can see respectively that you have actually the following. And then this is another parameter we need to determine using the m and also the delta polynomials by using actually the second, the third and also the higher order derivatives in that case, which is also shown here. And if you have a second order approximation, you go actually up to q is equal to 2. If you have a third order approximation, for example, you go from a fourth order system to a second order or to a third order system, you go all the way to the necessary approximation. And this is for the values of m, and you have also a similar form for the deltas, and this is also an approximation really close to that one. And then we will find then the solutions for the c and d coefficients by actually equating these two expressions, which is actually shown here. That is already mathematically, of course, stated in here. Okay, and of course we have again the q1, 2, 3 and up to the number of required to solve the unknown coefficients. Okay, let's look at an example. What we have is the following system given, which is a third order system. Again, we have the poles at -1, -2 and a -3. And the DC gain of this system is 6 over 1 times 2 times 3, so it is actually just 1. What we want is the following. Use the accurate approximation method to determine a lower order approximation for this system. And also determine the unit step response and also the Bode plot of the actual system and also the lower approximation. And compare the results. So, let's look at the solutions. Of course, they want the accurate approximation method. We will of course use also the simplified approximation method to also compare that with the actual system response. So, the simplified form of the approximation says actually remove the farthest pole while keeping the steady state value the same as in the original system. And we already discussed this, because this pole is very close to these two poles. The approximation actually in the brute force form will not give you a very accurate result, but we will do it anyway, and we will see what the difference is between the actual system, this approximated system, and also the very a little bit accurate approximation method we will do later on. Okay, what we do is the farthest pole in this case is -3. So we will need to delete that and also retain the DC gain. So removing this pole and accounting the effect for the DC value or the steady state value, we have the following transfer function. So you actually divide by 3 the numerator and also remove the pole at -3. So you will have this, and if you simplify this, you will have this one. So that's actually done. This concludes actually the approximation from the third order system to a second order system. So I will give that G sub L1. Alright, that's for the first approximation. Now let's look at the more exact approximation, which is an algebraic approximation method in this case. And again, we will rewrite the third order system such that the denominator is given as a polynomial and it has a constant term is 1. So which is actually the following. This is what is given. We will of course work out this parentheses. You will have then the third order polynomial in your denominator, and you will actually divide now this such that the constant here is 1. So you will actually divide by 6. So we'll have 1 plus 11 over 6s plus s squared and plus 1 over 6s cubed. So let's then look also at the more accurate approximation method, which is then the algebraic approximation method. What we do first is we rewrite the given third order system such that the denominator of that has a constant term which is 1. So what we have is this transfer function. We rewrite the denominator, so we will actually work out the parentheses here. You will have a third order polynomial, and you will divide out this term such that you have a constant which is 1. In this case, the 6 of course must be a 1, so you will divide the numerator and denominator by 6. You will have this expression, and that is now also your delta S polynomial we will use later on. So this is the expression. Okay, the approximate transfer function is then given by the following second order system. This is then the approximation, now in this case GL2, which has of course two parameters, d1 and d2. That is actually what we really need to determine. In this case, it is now given this polynomial m is then a denominator of this GL2. So 1 plus d1s plus d2s squared. So it is actually a second order system. Okay, since we solve for the unknown coefficient of a second order system, we have the following situation. This is the expression in order to determine the values of m, and we go actually for q to 1 and for 2. So we have actually two values for our q. And we did it also for the delta, so we also have an expression, and again for q is 1 and q is 2. So we will actually evaluate this for two values of q. Now if you do that, you will have this result in the table. So let's look at the first one. This one is, it says actually the zeroth derivative, which is actually this one. So actually don't differentiate, just take over what you have here. So that's actually 1 plus d1s plus d2s squared. And if you don't substitute in that for s is equal to 0, you will have just these two terms goes away, so you will actually only have 1. So that's actually the first one. The next step is the first derivative, so actually make this 1, so actually go for the k up to 1. So you will actually have then this expression, so actually the first derivative, and you will have then this one. So you will actually differentiate this one to s. This will go away, you will only have here d1, and this will be 2 times d2s. That's actually shown here. And again, you substitute for s equal to 0 here, and you will have this expression. In a similar form, you do that for the case 2 and for case 3. So that is actually what you have here. Now, similar form, you do that also for the delta, so you will have for case 0 to 1 to 2 and 3. Then you have again a zero derivative, so no differentiation, just take over this one, then differentiate, and you have this one, and so second derivative and third derivative. And of course you substitute for s0 and you will have these results. So those are the result what we have here. Okay, what do we do next is the following. Now for q equals 1, we have the following situation. This is the expression we need to solve, and since we have of course q is equal to 1, that means actually 2 times q here will be then m2. So this is the expression, and then we will go from k is equal to 0, 1 and 2, and you will actually have this expression. So what we have is in the following situation. You just substitute what you had. That is all actually the summary what we have just determined. You can see actually that we have these 4 values here for the m. If you do the substitution here, you will have then the following values in here. And if you do that simplified, you will have minus 2 d2 plus d1 squared. That's for m2. Now, if I do the similar form for the delta, again for q is 1, which means actually this will be of course 2 times q, and since q is 1, this is delta sub 2. And again the summation, and I will work out actually the expression here. Looking in the table here, I will have these values, and again if you work it out, you will have 49 over 36. That's actually what you have. Okay, that is the result here. What's the next? Now, we have now determined the values for M2 and the delta 2. We need to equate these two, and then we have the following expression. This is actually our first equation in order to determine the D1 and D2, because at the end, that is our goal. We need to determine the D1 and D2 such that the lower order approximation is complete. So that's the first step. Now we go to the next one, which is then for Q2. So for Q2, we have the following situation. Again, we use this table for our analysis. And then this will be, of course, 2 times Q. So it is actually 2 times 2 will be 4. And you will now go up to 4. So since this is now, of course, also 2Q. Then you have again the same expression. And you will now have more terms because you have now also a longer summation. Now, again, we will look at our table for this m values, and if you now substitute those just looking at a table, you will have this minus d2 squared. That's actually what the values of m4. Now, in a similar form, you can also do that for delta. Now, delta of 4, again, because it is 2 times q, and since q is 2, this will be a 4. And it will also go to 2q. Again, the summation, and we have more terms because the summation is longer. And we will use the data here in the second column of this table. Substitute the values, you will have this, and if you work it out, you will get minus 7 over 18. Now, again, as we did in the Q1 case, we need to equate the M4 and a delta 4. This is here, and if you do that, you will have minus d2 squared will be minus 7 over 18, and that will give you d2 is equal to plus or minus the square root of that 7 over 18, or approximately plus or minus 0.6236. That's actually the value now for d2. Now, since we know the value now of d2, we can also determine now the value of the d1 using the previous expression. Now, the coefficient of d1 is given by this expression. We have already determined that, so we can also see that from the previous analysis it was then determined, and by rewriting a d1 in terms of d2 you will have this expression. Now you can see that the d2 can be substituted in here. So first start with the positive one, and then we will do also the negative one. So for the positive one, and we'll just take the exact value, we will have this just expression here, and you will also have the negative one. So you will have this. So you will have 1.615, and the other one is minus 1.615. Now if you just do the similar way, but then take the negative value here, again, of course, the exact value, just substitute the values, you will have these two values. So we have now for d2 2 values, and for d1 actually 4 values. Now let's also now look at the sum of the results. We have now for d2 these 2 values, and these are the results for d1. So d2 result actually in these 2 values. So one is the positive one and another one is the negative one, and d2 also resulted in these 2 values. So what we do is, of course, we will need to have a stable system, and the negative values for the d1 and d2 will have a right half plane poles. So that will, of course, make the system unstable. So we will reject actually these results. So the solution will be only the part which is a positive for d1 and also for d2. So in this case, we will just, of course, take the d2 here, and that will also result in a positive value for d1. So this is the collection we will take, and we'll just reject the rest. So actually in this case the valid solutions are d1 is 1.615 and d2 is 0.6236. Now, having determined the d1 and d2, the lower order transfer function will be then given by this. This is of course what we have determined or set up at the beginning. And now we have the value of d1 and also the d2. Just substitute the values in here, you will have this. Now you can also rewrite this a little bit in a different form. So multiply the numerator and the denominator, such as the s squared, and all the s and the constant term is appearing here. And you can also place it in parentheses such that the poles are visible directly. Okay, that's what we have now for our system in a lower order approximation. What we also note here is the following. The poles of the original system, given original transfer function, was -1, -2 and a -3. You can also see that here. This is the original system. Now we have the poles at -1.024 and the other one is -1.565. So we have now actually made two new set of poles, and actually the third pole is gone. This is now a second order system and this was a third order system. Okay, let's also look at the simulation results. First we start with frequency response or the Bode plot. We have the following Bode diagram. You can see the three diagrams here. This is the original system, this is the brute force approximated system, and this is the more accurate approximated system. So these are also all shown here. This is the actual, which is a third order system. This is the brute force approximated system, so it is a second order system. This is also a second order system, but we have now a different location of the poles. So the orange one is farther away than the yellow one from this blue line. So the blue line is the actual system, that's the third order system. You can see the yellow one is closer to that than the orange one. So yellow one does a better job in the more accurate approximation than the brute force approximation. You can also see that in the phase plot. The orange one is farther away than the blue line, so the orange line, I mean the yellow line is more closely to the blue line. So you can see the approximation method does really do the job. It is not the best solution, so you can of course use a much better approximation method, which might be of course also a complex analysis, but this is already better than the brute force approximation. Okay, let's also look at the transient response, and specifically the unit step response, or the step response here in this case. What we have is now the unit step response. This is the time, this is now the amplitude and the response. You can see all of them goes to 1 because they have the steady state value of 1. You can see again, this is the original system, this is the brute force approximated system, and this is then the more accurate approximated system. Again, the transfer functions are shown here. So the G, GL1 and GL2. This is the more accurate approximated system. You can see again the blue line is the original one. That's the system. The yellow one is the more accurate approximated system. So that's actually also more closely to the blue line. So it is following that more accurately. And the dark orange line is not really accurate as that yellow line. So again, in this case, if you want to compare this, the yellow line does actually a better job by approximating this blue line. Of course, you cannot have that this will be exactly equal to each other, because you're already approximating and you will also lose some data. So your dynamics will be not exactly as the original system, but you will have already some more approximation which is better than the brute force form. And why we also do the second order approximation is because we have also in the second order approximation nice formulas to determine the settling time, the peak time, and overshoot, and all those elements to determine our specifications for our controller. So that's actually the benefit to have an approximation going from the second order to the, from the third order to the second order. Okay, this is now for this example about the approximation of a third order system going to the second order system. First we have to just use the brute force method, and then also use a more accurate algebraic approximation method to determine the transfer function. Of course, we will move on in another example where we see a more practical form of an example, but this was also an introduction to the topic and also with a very simple example. If you have any questions, of course, please let me know and I will try to answer them as soon as possible. Thanks again and see you next time. Take care.